Okay, welcome everyone to the FCCJ. My name is Tim Honyak. I'm a freelancer here, and today we're going to hear from two gentlemen from Japan's space agency, JAXA. It's always interesting to hear about developments in science and space. Recently we heard about the second Voyager probe leaving the solar system. In terms of Japan, what we're going to talk about today is the Hayabusa-2 mission, and I'll just introduce the guests briefly here. Dr. Kuninaka is director of ISAS, which is the department at JAXA, the space agency, which is responsible for these kinds of space missions. And Dr. Tsuda is the project manager in charge of Hayabusa-2. So please, gentlemen.
Yeah. Thank you very much. My name is Hitoshi Kuninaka. I'm very honored to be here and to report the recent topics of Hayabusa-2 mission. I would like to explain you something. Before the Hayabusa-2, we have another mission that is the Hayabusa-1. We call original Hayabusa. I was involved by Hayabusa-1 mission. I take charge of the development and operation of ion engine dedicated for Hayabusa original. But Hayabusa was too immature to cause a lot of malfunction and errors in space. But the achievement of Hayabusa stimulated the young generation and foster new engineer and scientists and the space community. And so supported by their people, we are now operating the Hayabusa-2 mission. So in the developing phase of the Hayabusa-2 on the ground, I, as the project manager, I organize these people to develop the Hayabusa-2 mission. And then so that we are now executing the very sophisticated proximity operation around the asteroid Ryugu under the support of the engineers, scientists, and the international community. And from now on, I would like to explain, Dr. Tsuda will explain you. So original Hayabusa-2 mission, we plan to execute first touchdown on the surface of the Ryugu in the end of this October. But due to some reason, we postpone touchdown operation in the several months. And then so now Hayabusa-2 team is making a workaround method to realize first touchdown operation. I believe their accomplishment. And then so I appreciate it very much if you pay attention to their effort and their clever approaches. Then Dr. Tsuda will present you in detail.
Okay, thank you. Dr. Tsuda, please.
Thank you and good afternoon. My name is Yuichi Tsuda, and I'm the project manager of Hayabusa-2. And I'm very pleased to brief about the latest mission status of Hayabusa-2. And before the project manager, I was the project engineer to lead the development of the spacecraft engineering-wise. So I am probably one of the clever young generation, hopefully. So first of all, let me start from this slide. The Hayabusa-2 is primarily a science mission to explore the brand new asteroid Ryugu, and also aiming at the enhancing the space exploration engineering by a sample return attempt to unknown celestial body. And there are two other fields that are strongly related to our mission. One is a planetary defense, how to protect the Earth from hazardous meteoroids, and also the planetary resource, how to utilize the resource in the other celestial body for the economic activity of human. So Hayabusa-2 mission is contributing to these fields by very unique technology, not only the in situ remote observation, but also landing, roving, sampling, and impacting. And I will touch these four later. So anyway, the spacecraft arrived at Ryugu on June 27 successfully. And since then, the spacecraft start hovering at 20-kilometer altitude and have done a lot of in situ observations. And this is the picture of the operation center exactly on that day. And since then, in the operation center, and since then we have been living in this room for day and night. 24 hours a day, 7 days a week, to take care of the spacecraft and also to investigate this brand new asteroid, Ryugu. And this is the Ryugu, how the Ryugu looks like. And it's 1 kilometer size in diameter. And the most interesting feature that we found first is its shape. So we call it the top shape. And actually, this shape is well known and typical for this kind of asteroids. But we haven't expected this shape for Ryugu. And as you may know, on December 3rd, the American sample return mission OSIRIS-REx arrived at Bennu, which also looks like the top shape. And which is even more exciting for us because we are collaborating with them. So probably we are sure that we can enhance our scientific outcomes by this strong collaboration with each other. And here are some quantitative initial scientific findings about the Ryugu. And I just marked 4 surprisings. The first one is its shape, as I told you earlier. The second thing is the spin axis orientation. So we thought before arrival that the Ryugu it has an inclined spin axis with respect to the orbital plane, but in reality it is upright, and that affects our operation scenario much. And the third surprising is its color. So it looks like very, very dark. So we usually show this kind of Ryugu picture, which looks rather bright and gray. But in reality, if you see with your naked eye, it's very dark. It's almost black. So we are just enhancing to make you see easier. And the fourth one, that's actually the headache for us. The surface is covered by numerous boulders and craters, so it's very, very bumpy. So that is now making us a lot of headaches. And after arrival, we have performed a lot of the in situ observation using the spacecraft remote science instruments. And after that, on August 17th, we held the key milestone meeting participated by all the project members. That is called a landing site selection meeting. This is participated not only by the Japanese scientists and the engineers, but also by the international partners, including DLR, CONES, and NASA, so world space agencies. And in this meeting, we decided the 3 spacecraft landing sites. One is a primary, and the 2 backups. And the 2 rover landing sites, the one is for Minerva 2-1 rover landing site, and the another is for the Mascot lander landing site. And this is only a one-day meeting, but and participated by the distinctive scientists from all over the world on the research about the asteroids. And what was impressive personally for me is that even though it's one-day meeting, we reached the perfect conclusion without any objection. And we decided these 3 landing sites. So the mission, this meeting was so smooth, although the Ryugu is not smooth. And as a conclusion, the Minerva 2-1 was decided to deliver to the northern hemisphere, the N6 site we call, and the Mascot lander was to deliver to the southern hemisphere, and Hayabusa2 is to land to the equator. And so before talking about each result, accomplishments of the each critical operations, I'd like to slightly touch the interesting feature, unique feature of the Hayabusa2 spacecraft. And Hayabusa2 is equipped with as many as 12 deployables, so that can be detached from the spacecraft in appropriate timing. So because of this unique feature, so this mission is attractive not only for professional engineers and scientists, but also I believe attracts the general publics. And among those 12, we already delivered 4 of them to the surface of the asteroid. The first one was the Minerva 2 rovers, which is composed of 2 robots, and that was delivered on September 21st successfully. And after that, on October 3rd, we separated the Mascot lander and delivered to the surface. And also, finally, we delivered one of the target marker. Target marker is used for the visual marker for the spacecraft landing in later, and we delivered one of them successfully on October 25th. Okay, so first of all, I would like to introduce about the result of the first critical operation conducted based on the landing site selection decision. The Minerva 2-1 operation was performed from September 20th through 21st, and 2 rovers were deployed to the asteroid surface at the same time. And these 2 are about 1 kilogram rover each, and it can hop automatically and do the surface activity and observe the asteroid surface by itself and send the data to the ground via spacecraft relay communication system. The operation was very successful, and right after the separation, the 2 rovers retrieved a lot of precious surface information to us. And this is one of the early pictures taken by the rover. And because these 2 are lived for more than expected period, we now can say that these 2 rovers have become the world's first robots which successfully performed mobile activity on the small body surface. And here are some pictures taken by these 2 rovers, and they can take a picture during the hop, and also even they can see the mother spacecraft from the rover, and that's on the right figure. It's a little bit difficult to focus because of the rapid motion of the rover. And of course, they could retrieve a lot of precious scientific information about the very microscopic structure of the surface, like these figures. And you can see very black and the rocky surface. And what we found, one of the very interesting feature on the Ryugu from these rovers are that the surface of the Ryugu is covered by not by sands, but rather by rocks and stones. So there are no smooth surface found by the Minerva 2-1 rover. That it's actually unfavorable for spacecraft landing in the future. And this picture is actually the movie taken by one of the rover, and you can feel as if you are standing on the Ryugu surface, and the sun is moving from the east to west. after the success of the Minerva 2-1 operation, we conducted the second lander deployment, which the Mascot lander. The Mascot lander was developed by DLR and Kunes, our German and French partners. And this is the largest lander equipped on the spacecraft. And this rover can also hop. But this is driven only by primary battery, so different from the Minerva 2 rovers, which is driven by solar array paddle. So this lander only lasts for 17 hours. So we have to more concentrate on this, carefully operate this Mascot, because there's only one chance. And we cannot accept a failure for these 17 hours of operation. And because this is they participated by the international partners like DLR, Kunes, and also NASA, ESA, and JAXA. So this is actually the largest operation organization we built in our Hayabusa2 operation. And the Mascot was operated by DLR and Kunes, but through JAXA Space Operations Center and also the JAXA's and NASA's, ESA's Deep Space Network. And also the Hayabusa2 worked as the relay to the Mascot. So all these are operated in a consistent way. So that led us the perfect success. And because the Mascot was only 17 hours live, 17 hours corresponds to actually the 3 asteroid days, because the asteroid period is about 7.6 hours. So the first day, the day 1, the Mascot was separated, and a few minutes later it successfully touched the ground, but with the upside down orientation, which is unfavorable for scientific observation of the Mascot. So in the next day, the Mascot team decided to do the big hop to flip its orientation to the appropriate orientation, and it was successful. And after that, Mascot started extensive surface observations for a whole asteroid day. And in the day 3, the Mascot team decided to do additional small hop to relocate the Mascot slightly to change its science observation site. And it was also successful, and the final data downlink was completed before the third night. And the battery was depleted after 17 hours of successful operation. And here are some outcomes from the Mascot operation. And this picture is a view from the spacecraft, the flying toward the asteroid surface. And this picture is on the right. You can see the pictures of from the Mascot camera, and the left figure is to show the trajectory of the falling Mascot viewed from spacecraft. So this kind of picture, we got this kind of very precious surface images from the Mascot as well. And this is another view, and this is one of the very highest resolution images that we have from the Mascot right before the initial bounce. And the Mascot team not only used this for the scientific interpretation of the Ryugu, but also they provided these images to us so that to help our spacecraft landing safety analysis. So we are not only collaborating in terms of science, but also for the ultimate goal of the whole project itself. So that's, I think, one of the very good, successful example of the international collaboration for the space exploration activity among big space agencies all over the world. And after that, we started working on the spacecraft landing. And for these we did for these 5 months, we conducted 7 GCP nav descents. GCP nav is a technique we applied for the precise terrain relative navigation and guidance for landing and the rover separations. And out of 7, 4 were low altitude access, less than 100 meters. And 6 were successful, and 1 was aborted due to an amateur LiDAR setting because the Ryugu was too dark. But based on these results, we now concluding that a latitude range of plus minus 30 degrees has been proved to be accessible with a higher than expected guidance accuracy. And this slide shows the place we accessed. We actually accessed in the past 4 low altitude descent. So we covered Northern Hemisphere by Minerva-2 operation and Southern Hemisphere by Mascot Operation, and additional 2 rehearsals on October 15th and October 25th to access to as low as 10-meter altitude. So the surface is almost there. But as the Professor Kuninaka said earlier, the problem is we had a problem in the Ryugu side. So the Ryugu, because the Ryugu is bumpy, the original accuracy of 15 meters is not enough for safe landing. So we are now obliged to narrow down the landing accuracy to as small as 20-meter diameter. So this is a 20-meter circle that we are now thinking that's a safe zone for touching down. And so because this is very narrow, we decided in the last October not to do the touchdown directly on October, but instead we decided to do the additional rehearsal to precisely evaluate our landing accuracy. And we postponed the touchdown to the next year. And this is the touchdown sequence the original touchdown sequence we thought. So at the altitude of 20 meters, the spacecraft is to release a target marker to the ground. And then after that, the spacecraft will try to hover at 20-meter altitude. And at the same time, by using flashlight, the spacecraft is trying to track the drop to target marker by using camera and flash. And try to keep the position always right above the target marker. And when its motion is converged, spacecraft finally tries to do the final descent to the ground and then collect the sample and then ascend. So this is the original plan. And what we actually did in last October was like this. So we wanted to test all the engineering aspects of landing except final descent. And we actually released a target marker, and by evaluating where the target marker lands, we can accurately evaluate where the landing accuracy of the spacecraft. And this is the computer graphics we made before arrival at Ryugu, so it's not actual Ryugu. It looks like very smooth, although in reality it's not. So we tried this operation on October 25th, and this is a movie we actually took during that operation. And this movie was taken from the spacecraft camera, and you can see the bright spot falling toward the surface of the asteroid, and that is a target marker. And because the spacecraft is always trying to keep the target marker at the center of the images, you can see that the spacecraft successfully track the target marker and hover right above it. And after that motion is converged, spacecraft started ascent. And actually, this is so successful, and this gave us a great confidence about our landing technique. So all we have to do is to do the final descent. And this is the resulting target marker position. And this is a 20-meter diameter landing site. And can you find the target marker? Which is here. And because it's very bright, it's easier for spacecraft to identify this target marker. And it's only 15.4 meters off from the center. So it's still not satisfactory, but it's far improved than the original design. So we are now still assessing how to make the touchdown utilizing this dropped target marker. And this is another movie we took at the landing rehearsal. And you can see very beautiful Ryugu while the spacecraft is ascending, and you can also see the shadow, self-shadow. And at the this one is a sampler horn, and in the actual touchdown, we will see the sampler horn actually touching on the surface, which which would be the evidence for we actually made a touchdown. So this is the list of the accomplishments so far. So we already delivered 2 rovers, Minerva 2-1, to the ground, and also we delivered the Mascot lander to the ground. And the upcoming event will be the touchdown that will be planned in early next year, and followed by crater forming operations in the middle of next year. So next year is a climax for our mission. So thank you very much. And after this, the Professor Kuninaka will give another talk, more general talk about the
Okay. So
future mission.
I'd like to explain you our ISAS strategy to explore solar system. We call the small body exploration strategy. So you may know these are our solar system. So the Sun and the Mercury and the Venus, Earth and Mars. So inside of our space, we have a rocky planet, and beyond Mars, Jupiter, Saturn, and Neptune, and so on. They are the gaseous planet. So beginning of the history of solar system, and Earth rocky planet were very hot, so that the gas and the water have already all of the gas and the water evaporated and gone away. But after the cool down of these rocky planet, so volatile material might be conveyed from the outside of our solar system, from the gaseous planet. And in that sense, on Earth, we have a lot of the water and atmosphere, and so such kind of the volatile material was conveyed by the minor body. They are planet, asteroid, comet, and the space dust. And so, so that is the hypothesis for the material transportation in solar system. And so we are focused on the small body exploration. So in order to reveal the history of solar system, 4.6 billion years. And then so we are now not only Hayabusa2, but also so many spacecraft. ISAS, our institute, is now delivering the lot of spacecraft into solar system. On October this year, we sent Pepe Colombo, a spacecraft, toward Mercury, and Akatsuki is now circulating around the Venus. And then so we are now developing the pinpoint landing mission of the SLIM on the surface of the moon. And then now we are operating Hayabusa2. And the future mission, we are proposing the MMX to the Japanese government. MMX means the Martian Moon Exploration Program. We want to pick up the some of material from the Martian Moon, Phobos or Deimos. And then so JUICE, that is the Jupiter mission. That is a joint mission with European people. and the Caesar, that is the comet sample return missions. And then so using the swarming technology, どうすればいいの？次のページ。なんかハングしてる。Okay, so final page. I want to show you the ISAS deep space fleet. So in the swarming manner, we want to reveal the solar system. And then so that is the deep space fleet, ISAS plan. So in 10 years, we want to realize such kind of the deep space fleet.
Okay. Okay, wonderful. Thank you very much. That was very interesting. Now, before we open the floor to questions, I'm going to ask a question, if I may. I was wondering if you could just explain a little bit more about the overall goal of the Hayabusa 2 mission. I understand one of the goals is to return a sample to the Earth. Now, you mentioned in the beginning how NASA's OSIRIS-REx mission is now at this asteroid called Bennu, right? And it has spotted signs of water. I'd like to know, has Hayabusa 2 spotted similar signs on Ryugu, the asteroid? And what kind of sample do you hope to return to Earth from Ryugu? Is it just a surface sample of rock, or please, could you talk about that a little bit?
Okay, thank you for a good question. And the OSIRIS-REx and the Hayabusa 2 are both aiming at the carbonaceous asteroid. So, which means that the asteroids are made of carbon organics. And the importance of carbon is, I think, obvious, because it's a material for the life on Earth, and the OSIRIS-REx mission is aiming at Bennu, which is a carbon-rich asteroid called B-type asteroid, and the Hayabusa 2 is aiming at Ryugu, which is C-type asteroid, which is another carbonaceous asteroid. And that's a few days ago. Actually, yesterday, they announced that they found the water, clue of water on Bennu, and we actually found a similar sign on Ryugu, but it's very faint. So compared to Bennu, it's not easy to identify it's really the water. So that's because we took a very long time to identify it. But now we are gathering the confidence on the existence of water also on the Ryugu. I think that's one of the very important key findings of 2 missions.
Okay. And as opposed to Hayabusa 1, which, if I understand correctly, returned a few very small molecules from the asteroid it visited, Hayabusa 2 could return larger samples.
Okay, are you asking about the difference?
Yeah, the difference between those. Yeah.
So it's the difference of the amount of the sample is due to the way we do the sampling.
Right.
So the OSIRIS-REx assumes that uses a gas to and then blow the surface, and then blow the flying sands will be collected by the sample collector. But the strategy we took for Hayabusa 2 is by using the projectile, and by ejecting the projectile in very fast to the ground, and the reflected soil will be captured by the sample collector. And our strategy is more appropriate for a wider range of the surface stiffness. So we don't have to assume any sands, existence of sands or rocks, because the projectile can hit and destroy somehow the surface. But because of that strategy, if the surface is made of sand compared to Osiris-Rex, we will expect less samples.
I see.
But Osiris-Rex is assuming that the surface is made of sand. So I don't know if it's how they can collect a sample specifically for Bennu. So that's I'm looking forward to that.
Okay. Obviously, there are very many unknowns and questions involved in these missions. But speaking of questions, I'd like to open the floor to anyone who has a question here about the mission. Please just put up your hand and come up to the microphone. Okay. In the meantime, I'll ask another question. You talked about the possibility of learning about planetary defense at the beginning, and how the Earth does face a threat from large asteroids that could impact, and some of these have caused devastating destruction in the Earth's history. What do you think we can learn about planetary defense when it comes to studying asteroids? Can we prepare for a major impact in this way?
Yeah, so every year tons of meteoroids coming into the Earth. So and most of them are very small, so it's not affect the surface. But sometimes it affects very severe damage to the surface. Like a few years ago, the big meteoroid drops to the Russian Chelyabinsk, and have some injury there. So if that kind of things happens, it's very dangerous for whole human beings. And nowadays, it's still difficult to protect from that if the meteor is very big. But at least we are getting the technology to identify or find that kind of hazardous asteroids prior to the actual impact. So we are now still studying or gaining the technology to find such hazardous meteors, but not in the level of protecting from that. But some people, some university and also United Nations are also seriously studying about how to protect the Earth from that kind of hazard.
Yeah. So some of the movie story, and so they use the atomic bomb to destroy the asteroid. But the present state, our observation from the Hayabusa 1, 2, and Osiris-Rex, so asteroid is very fragile material, so that the atomic bomb method is not appropriate. And then so
that's good to know.
One of the consideration, ion engine pushed away, so asteroid, it will take a very, very long time, but that is a very clever method. And then so that some of another people considering the another method, that is the gravitational tractor method, so that they will input the large amount of the spacecraft vicinity of the solar system, vicinity of the asteroid, and then so that the spacecraft and the asteroid interfere with the gravitational force, and then so using it manner, so spacecraft push or pull away of the asteroid. But in any case, this kind of method will take a very, very long time to change the orbit of the asteroid.
I see. Okay, we have a question here. Yes, sir.
Lars Nicolaisen, German press agency DPA. Thank you very much for your presentation. My question concerns your plans for the moon. Can you explain us what Japan plans to do on the moon? And my understanding is that in the future you hope for sending Japanese astronauts to the moon. First of all, is that correct? And when do you think that's going to happen? And if you can explain to us a little bit about the projects and the plans, what you plan to do on the moon and with the moon. Thank you.
Yep. So now we are operating the ISS, International Space Station, for the whole 15 countries collaboration. And then so ISS program will be terminated in the around 2024. And then so beyond ISS program, international people are now discussing about the future mission. So NASA has just proposed the Gateway mission. So that is a new small space station circulating around the moon. And then so that the name is Gateway. So it means that is a gateway to the surface of the moon and the Mars. And then so present state, Japanese government did not decide to participate in that program, but the JAXA is now considering how do we support the Gateway missions. And then so one of the approach is the we want to go to the polar region of the moon through Gateway. And then so you may know, polar region of the moon is a very appropriate location to sustainable working on the surface of the moon, because the polar region have solar radiation very, very long time. So and then so that that is a very good position to make a basement for moon activity. And then so in order to realize such kind of the moon base, we need technology to pinpoint landing technology. So such kind of very appropriate location is very, very narrow. So that we need technology to go to precisely landing. So in order to get such kind of technology, we are now developing the SLIM mission. So that is a pinpoint landing mission. We will execute such kind of mission around 2021.
Okay, another question, please.
Hi, Tilina from Earth Life Science Institute. I was wondering, so Ryugu is not like, it doesn't have the moon, the fine grains like in the moon. And so it's very rocky and you have a lot of boulders. So I was wondering how prepared you were when you were designing the spacecraft, especially for the landing. Did you think about the surface already that you might actually expect something like this?
Yes. So we first of all we are now we already observed extensively observed the potential landing site with a very high resolution, and for that purpose we descend to very low altitude for the high resolution observation several times, and also taking advantage of the other critical operation like Mascot Operation and Minerva Operation to take a picture of the very close look images. And so first of all, by doing in that way, we want to know as precisely as possible how the landing site looks like and how safe it is or how dangerous it is. And the other thing we did is, like I explained, we wanted to accurately evaluate the landing accuracy. And so for that purpose, we actually dropped the target marker. And we still now the result is the landing accuracy of around 15 meters, and that is still not enough. So we are now trying to change the strategy so that the originally the spacecraft is to follow the falling target marker to make the landing, but instead of that, we are now thinking about utilizing the already dropped target marker, because it's a very clear visual marker on the surface, and we already know that where it is very accurately. So by telling the spacecraft that the target marker is there, then the spacecraft can probably do the precise landing using that target marker. So that's not that strategy we are now thinking.
Okay, any other questions, please? I was wondering if you could tell us a little bit more about why exactly you're waiting. I think if I understand correctly, you know where you want to land on the asteroid, but is it a question of making sure everything is precise enough? Then you will actually start the landing. Is there a key piece of information that you need before you can say, okay, now we are ready to try to land?
Yes, so there are two things. The first is that we have to wait because we are in actually bad geometry at this moment for about 1 month, because the spacecraft is in the same direction as the sun, viewed from the Earth, and actually the spacecraft and asteroid is exactly on the back side of the sun. So we cannot communicate well with the spacecraft at this moment, and actually we are taking advantage of that opportunity for our thinking time. And the second reason is we are obliged to change our landing strategy because it's too bumpy. So we have to improve our landing accuracy to. Originally, it was 50-meter accuracy, but we have to shrink down to less than 10 meter. That's quite challenging engineering-wise. So that's why we are taking time for the preparation.
Okay, interesting. You mentioned before about how you're spending long days and nights in the Sagamihara Space Operations Center. Could you talk a little bit about what it's like to handle the practical problems of controlling a spacecraft that, if I'm not mistaken, is hundreds of millions of kilometers away, if that's accurate. And what about the number of people involved in working on this project? How many people are actively helping with the mission right now, and how do you coordinate all those people?
Okay, so the spacecraft is now 300 million kilometers away from the Earth. So it with the speed of light, it takes about 20 minutes. So every time we command the spacecraft, it takes 20 minutes so that the spacecraft can then follow that commands and return the answer to the Earth another 20 minutes later. So it's very slow operation, and we are always taking into account that round trip delay for our operation, and the operation usually in general case, like the peaceful day without any critical operations, the operation room is occupied by only 4 or 5 people, and that's the minimum people for the operation, the daily operation. But for critical operations like landing and rover separation, there are as many as like 40, 50 people in that room to take care of from each expertise.
I see.
Yes, and but if we count a whole project member, it's actually difficult to count. It depends on how we count the member, but it's if we count the people who we can directly reach by phone or email, that's about 600 people.
Wow.
International people are also there.
Okay, interesting. Yes, sir.
Hi, Simon Denyer from the Washington Post. So just wondered, when you actually land Hayabusa on the asteroid, what are the questions? I mean, you said some of the findings that you've discovered so far. What are the sort of remaining questions that you want to answer? Are there things you still want to find out about the asteroid, or is it more a question of just finding the sample now and bringing it back?
So your question about the after the touchdown?
Yes.
Yes. Okay. So the touchdown itself is for the future investigation after the spacecraft returned to the Earth with that sample. And but after the sample collection, we are planning to do another touchdown to different sites, and that may increase the scientific value, because just a one-time touchdown is to know about the one place on the surface. But if we do the multiple landing, we can know better about the variety of the variation of the surface. But we are still have not decided if we really do attempt the second touchdown. And in addition to the touchdown, we are planning to make a hole on the surface of the asteroid by a kinetic impact. And that's the new attempt, which we haven't, the world first attempt, I mean, to make a crater on the surface of asteroid. And by doing that, we are expecting to have a few meter crater on the surface, and we will expect to have the exposed material, so we can observe that kind of a subsurface material from the spacecraft. And also, if the situation allows, we want to try to touch down in the vicinity of that crater, so that we can collect the sample from the exposed material. And that's very, very challenging, but still we are looking at that.
I think that's quite a fascinating part of the mission. In the briefing I went to in October, I think you showed a slide or a video about how you hope to blast a crater in the asteroid with an explosive charge, if I'm not mistaken. And there was an image of a Hayabusa probe moving away from the asteroid to protect itself. Is that still a realistic?
Yeah, actually, this is a movie for that.
Okay.
So this is the small carry-on impactor aboard the spacecraft, and it is to be separated. And this is to detonate, and before that, spacecraft has to escape because it's dangerous. And after the escape, that impactor detonates and hit the surface and make a hole. And we want to observe how the crater is formed. And after that, we will do the extensive observations of the new crater. And if situation allows, we will try like this. But this is really a hope.
Okay, interesting. Okay, if there are no more questions, I'm going to wrap it up here. Perhaps you could all join me in thanking our guests today. And as is the custom here at the FCCJ, we give each one an honorary membership. So thank you very much, Dr. Kuninaka and Dr. Tsuda. It's been a pleasure, and we hope to have you back here soon. Thanks very again.